Welcome to the second part of your lecture, in which we're going to discuss data link layer switching. We will discuss uses of bridges, learning bridges, spanning tree algorithm, virtual LANs, and interconnecting devices. A bridge is layer 2 device that is used to connect multiple LANs. It can be used as a backbone or to connect two LANs together. Bridges are used because different organizations have different LANs, so to connect different type of LANs. Different locations have different LANs, so to extend the geographical space of a LAN. Multiple LANs are used to extend physical distances, and multiple LANs are used to accommodate the load, so the bridge will divide the load. Different LANs are used to increase security, so connecting different LANs will maintain different security domains. Different LANs are used to increase reliability, so a bridge will ensure that the collision domain and the failure domain are distributed. One use of a bridge is actually to connect two different LANs as Ethernet to a wireless LAN, where the packet is sent to the logical link control in the wireless LAN. The logical link control will send it to the medium access control sublayer. The medium access control sublayer will encapsulate it in a frame and send it to the physical layer. In the bridge, the packet is extracted and re-encapsulated in Ethernet frame and sent to the Ethernet. The problem is different networks such as Ethernet and wireless LANs have different format of frames. The bridge can translate from one format to another format. Some common problems that a bridge can solve is, as we have said, different frame formats, and interconnected LANs don't run the same data rate. Say fast Ethernet and gigabit Ethernet. Different LANs have different maximum frame length. The same applies for 802.11 and 802.3. And some LANs at like 802.11 support encryption, while Ethernet does not support encryption. Wireless LANs support quality of service, so does the token ring, for example, while Ethernet does not support quality of service. The bridge is used to translate or to connect all these different LANs. The bridge can be used to connect two LANs or as a concentration point for connecting point to point, creating point-to-point links with the stations. The first is shown in figure A and the second is shown in figure B. A bridge also can be connected to a hub. The first 802 bridge is a learning bridge or the transparent bridge that have a large hash table inside the bridge, consists of all the possible destinations and tell which output line or which LAN it's belonged to. When the frame arrives, the bridge must decide which port it will send it to. If it doesn't know which port it will send it to, it will use a flooding algorithm. Learning bridges or transparent bridges learns about the network topology. When the first bridges are plugged in, the hash table is empty. None of the bridges knows where the destinations are, and it uses a flooding algorithm. That's to say, the frame will be sent to all other ports except the one it came from. And as the time goes, the bridges will learn about the destinations from the incoming frames, which in a process called backward learning. Every time a frame whose source is already in the table arrives, the entry is updated. and periodically, not updating the entries that are not updated will be flushed away in a process called aging. Learning bridges have routing algorithm for incoming frames depend on land that it arrived from and the land it's sent to. If the destination and the source lands are the same, it will discard the frame. If the destination and the source land are different, it will forward the frame. If the destination is unknown, it will use flooding. Sometimes redundant links are used to increase reliability. In the example below, a parallel link is used to connect bridge 1 and bridge 2. If A sends frame 0 to B1 and B1 does not know where the destination is, it will flood the frame into all its outgoing ports. Here it will copy to F1 and F2. When it reaches B2, if B2 does not know the destination, it will also flood the frame to all its ports, copying it to F3 and F4. F3 and F4 will reach P1. P1 does not know where the destination is. It will flood it again, creating F5 and F6, and this will create an infinite loop. Because the redundant topology contains loops, there should be a solution for this. The solution is the spanning tree algorithm, where the connected bridges are forming a tree with a root bridge that a tree spans from it, and all the links that might cause loops are eliminated. To build the spanning tree, the bridges have to choose the root bridge. The root bridge will be chosen as the one with the lowest serial number in the MAC addresses, and then there will be calculations for the shortest path from the root for every other bridge. That's how the spanning tree is created. If a bridge fails or a LAN fails, there will be recomputation. The creator of the spanning tree algorithm wrote a poem about the spanning tree. It's a very nice poem and we'll share here. I think I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity, a tree which must be sure to span so packets can reach every LAN. Third, the root must be selected by ID it's elected. Least cost paths from root are traced in a tree that paths are placed. A mesh is made by folks like me, then bridges find the spanning tree. So historically, 10 base 5 LANs were replaced by 10 base D LANs. Some used category 3 unshielded twisted pairs, and some used category 5 unshielded twisted pairs. But the whole thing has gone like this. Every adjacent offices were connected together to a hub, then to a switch, in total disregard for the organizational structure. Although hubs and switches can be used to resemble the organizational structure, sometimes it's not possible if the station was placed in another building or the station was too far away from the hub or the switch. So there is a need for us to have a way to resemble the organization structure other than the physical layout. Why do we need multiple LANs with restricted scope? for security purposes, where the broadcast mode, where everyone can hear the traffic, and we need to limit this to the people who are concerned with the traffic. To balance load, because when the stations are too many, the network will be overly loaded. And for broadcasting to the, let's say, intended stations. The other question is how to dynamically move a user from one LAN to another. This can happen by pulling out the plugs and pushing them back, or using virtual LANs, IEEE 802.1q standard. Virtual LANs are virtual LANs, local area networks that does not follow the physical architecture, but have their virtual architecture. To set a virtual LAN, the network administrator designed how many VLANs there will be, which computers will be on which LAN, and which every VLAN will be called. VLANs are marked named by colors, usually, since it's possible to print color diagrams showing both physical layout and virtual LANs layouts. Virtual LANs, to function correctly, there should be configuration tables set in the bridges or switches telling which device belongs to which virtual LAN. A port may be labeled with multiple colors, as we can see here. We have gray LAN and white LAN, and bridge 1 port is colored with gray and white because it receives traffic from both gray and white virtual LANs, while bridge 2 is colored only in gray because it receives and sends only to the gray virtual LAN. How can bridges and switches know about what color the incoming frame is? One option is for every port to be assigned a certain color for the VLAN. This is not good because, as we have said, there might be a need for multicolored ports, or every MAC address is assigned to a VLAN color. This is a possible solution, but it will restrict us more. Or every layer 3 protocol or IP address is assigned a virtual LAN color, and this is not an elegant solution. Better than this is to have tags, where a frame is tagged with the color of the virtual LAN it's coming from, but that means to add a new field to the frame, and it was done with the IEEE 802.1q standard, but both frames existed, the traditional and the new one with the tag field, and they are now bridges and switches and stations that are VLAN aware, and others that are traditional, which are not VLAN aware. The new frame has a tag field, as we have said. This tag field has a VLAN identifier and a priority field, which is not a part of the VLAN scheme, but it was added for the purpose of having quality of service. We have been talking about several devices for internet working, such as hubs, repeaters, bridges, switches, routers, and gateways. In this part of our lecture, we will have a look into each one of them. Application layer has application gateways, transport layer has transport gateways, network layer has routers, data link layer has bridges and switches, physical layer have repeaters and hubs. Repeaters are amplifiers that connect different segments of the cable. They take the incoming signal and amplify it and retransmit it. Hubs are, on the other hand, is a number of input lines joined electrically. Frames arriving from any line are sent on all the other lines. If two frames arrived at the same time, they will collide, and the collision domain is all the stations connected to the hub. The hubs have nothing to do with the MAC addresses or upper layer addresses, and they don't amplify incoming signals. Bridges, on the other hand, are there to connect two or more LANs. They inspect the frame header to know the destination and the source addresses, and they might connect different LAN types or LANs from different speeds. The bridges, each port has its own collision domain. Switches are complicated bridges, or are similar to bridges in how they route frames, and each port has its own collision domain. Switches never lose a frame because they buffer frames. If frames comes faster than they are retransmitted, the switch might run out of buffer and it would start discarding frames. This is why the modern switches use what we call cut-through switches. They are starting forwarding frames as soon as the destination header comes in before the rest of frame come in. As you can see here, the hub is a concentration point for all the stations that are linked to it. A bridge connects two LANs together, and a switch creates point-to-point links with all the stations. Routers are layer 3 devices. They inspect the packet header for the layer 3 addresses, IP addresses, for example. The routing algorithms are such as RIP, Open Shortest Path First, that we will examine in the next chapter, and they provide quality of service. Gateways, is a term that is used loosely. We have here transport gateways that connects two computers that have different connection-oriented transport layer protocols, such as TCP/IP and ATM. And application gateways, these are content-aware gateways that can understand the content of the message and translate it. For example, from an email to an SMS message for mobile phones. Your reading assignment this lecture is sections 4.5 and 4.7 from chapter 4, Computer Networks, Andrew Stewart Tannenbaum, and your writing assignment is Bluetooth. Thank you very much and see you in the next lecture.